Hello everyone, I'm Fabio Rossi, technologist at National Institute of Physics in Genova, Italy. I work in the FAIR project for SPOS6 and I'm going to show you our research in the data reduction with AI in the field of high energy physics. This data reduction strategy could be applied to many different experiments, but will focus on BDX. BDX is an experiment at Jefferson Lab in Virginia, US, specifically designed for dark matter research. This experiment could not imply the standard triggered acquisition systems because, making decision only on some sector of the detector, it's prone to lose some of the very rare dark matter events. For this reason, the new streaming readout techniques, in which all the channel could be part of the trigger, must be employed. But the main drawback in this scenario is the high data rate and therefore the needs of a data reduction strategy. With the assumption that no network devices have to deal with the signals, we can imagine this block scheme with a compression node at the very beginning and a decompression at the end, or only if we need the signal for the elaboration. We can store, for example, compressed data to save memory space. The chosen algorithm for data reduction is an autoencoder, an unsupervised machine learning algorithm based on artificial neural network. It is composed of two parts, an encoder to reduce the dimensionality of the input to a latent space, and a decoder to reconstruct the original signals. This process is lossy, but the loss could be managed and monitored during the process. For example, if a loss of a signal is too large, as for example in these cases, the signals could be sent uncompressed and an alert could be set. Later, an expert operator could be manually inspect the particular signal in the optic of Symbiotic AI. Some tests are carried on to define the best configuration, varying the latent space dimension or the number of layers. In this stage, a configuration with 2 layers and a latent space of 12 is chosen to keep a simple model for the hardware implementation, but with a little loss in the reconstruction. In this section, I report some results. First of all, the error introduced in the signal reconstruction. This is the error histogram of the entire dataset for single pulses in blue and for double pulses in orange. We can see also some extracted signal from the lower part of the histogram with a perfect overlap with the original signals, both for one and double pulse. But more interested, the signal extracted from the higher error tail of the histogram. Despite a few percent of error, the signal are overlapped as well. The advantage in comparison with the standard gzip compression are clear, especially for the estimated working zone, from tens to hundreds of signals. The compression factor for the autoencoder, in this case 4 times, is only a parameter and not depends on the number of signals to compress. In conclusion, some consideration about the execution time on different hardware. GPU and Alveo V70 FPGA boards are not suitable for this kind of model because the memory transfer overhead cancel all the benefit of parallel execution of code. On the other hand, an optimization of the C code implementation with multithread reach timing below 1 microsecond, and it is suitable for the application. Anyway, further studies are in progress in order to implement on low-level code on FPGA board to achieve higher throughput with less resources, employing, for example, FPGA standalone board. This is my conclusion. Thank you for your attention.